Right at the very edge of our solar system, there's a wall. Not a wall of rock or metal or any solid material at all, a wall of superheated plasma reaching temperatures between 30,000 and 50,000 Kelvin. That's somewhere between 54,000 and 90,000 degrees Fahrenheit, making it 5 to 9 times hotter than the visible surface of our own sun right now, today. Nobody predicted it would be anywhere near this hot or this complex in its full layered detail. And the only reason we know it exists at all is because Voyager 1 passed straight through it, survived completely, and sent the data home across 25 billion kilometers of empty space, taking 23 full hours just for the signal to arrive. Subscribe right now before we go any further, because everything you think you know about the edge of our solar system is about to get a great deal more interesting. Let's start with what most people actually think the edge of the solar system looks like, because the popular picture and the measured reality are very different things. The mental image most people carry is something like a simple boundary line, a clean edge, where the sun's planets stop and empty space begins. Maybe at Pluto's orbit, maybe a bit beyond that, but the actual edge of the solar system, at least in the physical and magnetic sense, is nothing like that. It is not at Pluto. It is not even close to Pluto. The boundary where the sun's influence truly ends sits roughly 3 times farther out than Pluto's average orbital distance. And when you actually reach that boundary and measure what's happening there, what you find is not a quiet, peaceful transition into calm, empty space. What you find is one of the most energetically violent, magnetically strange, thermally extreme zones in our entire cosmic neighborhood. Scientists call this entire outer structure the Heliosphere, a vast, roughly bubble-shaped region of space carved out by our sun and filled with the solar wind, the constant outflow of charged particles, protons, and electrons that the sun blasts outward in all directions. This solar wind travels at speeds between roughly 400 and 800 kilometers per second and carries the sun's magnetic field with it, stretching that field outward across the entire solar system like an enormous invisible web. The heliosphere protects the inner solar system, including Earth, from the harshest galactic cosmic rays, highly energetic particles accelerated by distant supernovae and other violent events across the galaxy, which the heliosphere's magnetic field deflects and slows before they can reach the planets. NASA describes this protective role directly. The solar wind ultimately travels past all the planets to roughly 3 times the distance to Pluto before being impeded by the interstellar medium, forming a giant bubble around the sun and its planets known as the heliosphere. But the solar wind cannot expand outward forever. Eventually it runs into the material of interstellar space, the gas, dust, and plasma filling the space between stars, itself under pressure from other stars, solar winds, and the large-scale dynamics of the Milky Way, where the outward pressure of the solar wind exactly balances the inward pressure of the interstellar medium. The solar wind stops. That balance point, the invisible outer boundary of the sun's magnetic domain, is called the Heliopause. Before Voyager 1 and Voyager 2 reached the Heliopause, scientists had theoretical models of what it would be like. Those models agreed. On the broad picture, a region just inside the Heliopause called the heliosheath, where the solar wind slows and turns turbulent. The heliopause itself is a transition zone, and beyond it, interstellar space. But the details, the exact temperature, the magnetic field behavior, the thickness and complexity of the boundary, were genuinely unknown until a spacecraft measured them directly. It's worth walking through the full layered structure Voyager 1 crossed on its way there, because each layer added its own surprises. The innermost zone is the solar system itself, where the solar wind flows outward relatively smoothly. Beyond the planets, the wind keeps thinning and slowing but remains supersonic until it hits the first major boundary, the termination shock, where the outward-moving solar wind is abruptly slowed from supersonic to subsonic speeds by resistance from the interstellar medium. Voyager 1 crossed the termination shock in December 2004 at roughly 94 astronomical units from the Sun. Scientists had predicted it would exist somewhere in that region, but the precise distance was unknown until Voyager measured it directly, seen in the data as a sudden change in the speed, temperature, and density of the surrounding particles. Beyond the termination shock lies the heliosheath, the turbulent, compressed, chaotic zone between the termination shock and the heliopause, where the solar wind has slowed, heated, and become highly turbulent as it piles up against the outer boundary. Voyager 2's plasma instrument, which Voyager 1 lacks since its equivalent failed early in the mission, measured heliosheath plasma temperatures, varying between roughly 20,000 and 200,000 Kelvin, far exceeding earlier model estimates. That was an early sign that the outer solar system's thermal environment wasn't as calm or predictable as theory suggested. Voyager 1 spent roughly 8 years crossing the heliosheath from 2004 to 2012, moving from 94 to 121.7 astronomical units, detecting numerous outbound shock waves, bursts of solar activity, and turbulent magnetic fluctuations along the way. A genuinely chaotic, energetically active zone, rather than a quiet transition layer. Then, in the final stages of that crossing, something even stranger happened. In the months before reaching the Heliopause, Voyager 1 entered what NASA scientists call the Heliosphere depletion region, a thin layer just inside the Heliopause where particle density dropped dramatically, and the magnetic field strength increased, as if the solar magnetic field was being compressed against the Heliopause from the inside, like pressing on a balloon and watching the skin thicken at the point of pressure. Some models had partially anticipated this, but its specific properties surprised the team. Then came the crossing itself on August 25, 2012, at 121.7 astronomical units, when Voyager's instruments recorded an abrupt, unmistakable change. The flux of low-energy heliospheric particles, solar wind material that had surrounded Voyager since launch, dropped to near zero. The flux of high-energy galactic cosmic rays jumped sharply upward. The magnetic field direction shifted, and the plasma density, measured indirectly through the plasma wave system, jumped by roughly a factor of 40, from about 0.02 electrons per cubic centimeter inside the heliosphere to about 0.08 outside it. Voyager 1 had crossed the Heliopause. It was in interstellar space, and this is where the wall of fire enters the story. As both Voyager spacecraft approached and passed through the Heliopause, their instruments measured temperatures of 30,000 to 50,000 Kelvin, 5 to 9 times hotter than the visible surface of the Sun, which sits at roughly 5,800 Kelvin. It's hotter than most of the hot phases of the interstellar medium astronomers had cataloged through remote observation and concentrated right. At this boundary zone, in a region so energetically extreme that journalists quickly nicknamed it the Wall of Fire. But let's be precise about what that phrase actually means, because it can mislead people. If you hear 50,000 Kelvin, you might picture something like the inside of an arc welder, something that would instantly vaporize a spacecraft passing through. Here, the temperature is real, but the danger isn't. The reason is a fundamental distinction between temperature and heat. Temperature in a plasma measures the average kinetic energy of individual particles, essentially how fast they're moving. At 50,000 Kelvin, those particles move extraordinarily fast. But if the plasma is also extremely sparse, very few particles per cubic meter, then even though each particle carries a lot of energy, the total thermal energy that can transfer to an object passing through is negligible. That's exactly the situation at the Heliopause. Extraordinarily hot in the kinetic sense, but extraordinarily thin, so sparse that Voyager's body and instruments are essentially never struck by particles. NASA confirmed this directly, noting that the extreme temperatures pose no threat to the probes due to the near vacuum conditions. The heat comes from particles moving at high velocity, not from dense, thermally conductive matter, the way heat works in everyday experience. Voyager passed through a wall of fire in the truest physical sense and emerged completely unharmed, simply because that fire was made of almost nothing. What caused this extreme temperature in the first place? The current understanding involves two related processes. The first is compression. As the solar wind slows and piles up against the Heliopause, its particles compress together, converting kinetic energy into thermal energy. The second is magnetic reconnection, when two regions of magnetized plasma with oppositely oriented field lines are pushed together. Those field lines can break and reconnect, releasing and particle acceleration. The Heliopause is exactly the kind of place where solar and interstellar magnetic fields meet and interact, making it a natural site for reconnection. Together, compression and reconnection produce a zone of superheated plasma that far exceeded what earlier models predicted for peak temperature and complexity. There was a second major surprise at the Heliopause, with perhaps even deeper implications. When Voyager 1 measured the magnetic field direction just after crossing, it found that the field in the very local interstellar medium just outside our solar system is oriented roughly parallel to the field inside the heliosphere. Voyager 2's crossing in 2018 confirmed the same thing. This was unexpected. Scientists had assumed the interstellar magnetic field, shaped by the large-scale dynamics of the Milky Way, would point in whatever direction galactic processes had set, independent of the Sun's own field. Finding the two, roughly aligned, suggests our local interstellar environment has been shaped, at least partially, by our own Sun's magnetic influence extending outward into the galaxy, that the Sun's magnetic reach goes deeper into interstellar space than models assumed, warping the surrounding galactic field over billions of years. NASA officially confirmed the significance of this alignment, explaining that it gives scientists new insight into how the Sun's magnetic influence extends into interstellar space, and that it challenges previous assumptions about how the Sun interacts with its surroundings. It suggests the interstellar medium immediately around our solar system isn't truly pristine, undisturbed galactic material. It's material shaped, compressed, and magnetically ordered by our sun's presence over an enormous span of time. The Heliopause also turned out to be less of a fixed, sharp wall than earlier models described. And NASA explained that it can move as the sun's activity changes, something like a lung expanding and contracting with breath. Evidence for this comes from the fact that Voyager 1 and Voyager 2 crossed the Heliopause at noticeably different distances. Voyager 1 at 121.7 astronomical units. Voyager 2 in 2018 at roughly 119, slightly closer to the sun. That difference is consistent with the Heliopause shifting inward and outward as the solar cycle drives changes in solar wind pressure. During high solar activity, a more energetic wind pushes it outward. During quieter periods, interstellar pressure pushes it back in. The Heliopause. Density. Both Voyagers measured near the boundary adds to this picture too, suggesting the interstellar medium presses against the heliosphere more actively than earlier models captured, squeezing it from outside, while the solar wind pushes from inside at the same time. Before going further, it's worth dwelling on one of the most profound things this crossing revealed, not about the boundary itself, but about what it had been protecting us from all along. One of the most dramatic changes Voyager 1 detected was in galactic cosmic rays. High-energy particles, mostly protons and atomic nuclei, accelerated to extraordinary speeds by supernovae, pulsars, through the galaxy in all directions, and they're genuinely dangerous. A human exposed to the full, unshielded cosmic ray environment outside the heliosphere would receive far higher radiation doses than inside the solar system. Inside the heliosphere, the sun's magnetic field and solar wind deflect and slow many of these particles before they reach us. Voyager 1 measured the cosmic ray flux just inside the Heliopause, then crossed it. And on the other side, that flux jumped something scientists had theorized for decades but never witnessed firsthand. The heliosphere isn't just an abstract structure, it's a real measurable radiation shield, and the Heliopause is where that shield ends. None of this would have been possible without the extraordinary engineering behind these spacecraft. Voyager 1's instruments were built to survive the cold vacuum of space for years, not decades. Its power comes from 3 radioisotope thermoelectric generators loaded with plutonium-238, a radioactive material that decays and produces heat, which the generators convert into electricity. At launch, they produced around 470 watts. By 2026, after 49 years of continuous decay, they produced less than half that. To manage the shrinking power budget, engineers have been shutting down instruments one by one, trading capability for longevity. The cosmic ray subsystem went dark in February 2025, and the low-energy charged particles experiment followed in April 2026. What remains active are the magnetometer and the plasma wave system, which have been measuring the magnetic field and plasma environment of the very local interstellar medium since 2012. The instruments behind the 2026 papers still being published about what Voyager 1 is measuring on the far side of the wall. The other half of this story that rarely gets told is the Deep Space Network, the global system of enormous dish antennas NASA uses to maintain contact with its most distant spacecraft. The largest antennas are 70 meters wide, roughly as tall as a 20-story building, and among the most sensitive radio receivers ever built. They have to be, because Voyager 1's transmitter produces only about 22 watts, roughly the power of a refrigerator light bulb. By the time that signal crosses 25 billion kilometers and reaches Earth, it's so diluted it carries virtually no energy, and the antennas have to strain to detect even 1 bit per second. The maximum data rate is around 160 bits per second. Everything humanity has learned about the wall of fire, the Heliopause, and the magnetic field behavior at the edge of our solar system has arrived through that trickle of data, assembled bit by bit over years of continuous listening. That's what makes Voyager 1 so extraordinary in 2026. It isn't just a heritage mission kept alive out of sentiment. It's the only direct, in situ scientific instrument humanity currently has operating inside the interstellar medium, measuring the environment on the years ago. Every new paper about the very local interstellar medium, every new model of the Heliopause, every new finding from IMAP about the energetic neutral atoms streaming inward from the heliosphere's outer boundaries depends in some way on the measurements Voyager 1 has been accumulating since its crossing. What makes this so scientifically important right now is that everything Voyager built up about the Heliopause is directly feeding into NASA's current active mission, IMAP, the Interstellar Mapping and Acceleration Probe, launched in 2024 and now operating near Earth. IMAP studies the heliosphere's boundaries by detecting energetic neutral atoms, particles created at the outer edges that can travel inward without being deflected by magnetic fields. But to correctly interpret those signals, scientists need to know the actual temperature, density, and magnetic environment at the Heliopause and just beyond it. And the only source of that ground truth information is Voyager 1 and Voyager 2's direct measurements. In that sense, Voyager, at 167 astronomical units and counting, is an active contributor to current NASA science, not a relic. And Voyager 1 is still going. As of 2026, it has shut down 2 more instruments to conserve its dwindling power: the Cosmic Ray Subsystem in February 2025, and the Low Energy Charged Particles Experiment in April 2026. Its magnetometer and plasma wave system remain active. A carefully planned power management upgrade, nicknamed the Big Bang, is being tested on Voyager 2 in mid-2026, with the goal of keeping both spacecraft alive into the 2030s. By November 18th, 2026, Voyager 1 will reach a distance of 1 full light day from Earth, a milestone never reached by any human-made object, and it will still be transmitting its thin 22-watt signal home across that gap, still measuring the magnetic and plasma environment of the interstellar medium it has been drifting through for nearly 14 years. The wall of fire it passed through in 2012 turned out to be not a wall at all, in the solid, hard sense of that word, but a living, breathing, magnetically active interface between our solar system and the rest of the galaxy, hotter than most people imagined, more dynamic than most models predicted, more protective than most people realize, and rich enough with unexpected physics that scientists are still publishing peer-reviewed papers about its downstream effects in 2026. No physics textbook written before Voyager passed through it fully described what was there. No model predicted the precise temperature range, the surprising magnetic alignment, or the full complexity of the layered structure on both sides of the boundary. Only direct, in-person measurement could reveal those things. And a 49-year-old spacecraft, running on the power of a refrigerator bulb, built on a workbench before the personal computer existed, provided those measurements 160 bits per second at a time, across 25 billion kilometers of empty space, in a mission that was supposed to last 4 years, through a wall that turned out to be both hotter and less dangerous than anyone expected, into territory no physics textbook had ever fully mapped. To put Voyager 1's distance in perspective, it helps to compare it to everything else humanity has ever sent into space. The International Space Station orbits a few hundred kilometers above Earth. Even Mars, at its farthest from Earth, is only a few 100 million kilometers away. Voyager 1, by contrast, is now more than 25 billion kilometers from home, a distance so large that light itself, the fastest thing in the universe, takes over 23 hours to cross it in one direction. Send a command today, and the earliest possible reply arrives nearly 2 full days later. Every single instruction NASA's engineers send to Voyager 1 has to account for that delay, planning each command sequence with the knowledge that by the time it's confirmed to have worked, an entire day and a half will have already passed. There is no real-time control of Voyager 1 anymore, and there hasn't been for decades. Every operation is a carefully scripted, one-way leap of faith across the solar system's outer edge. That distance is also why the wall of fire discovery took so long to fully understand. It isn't the kind of finding that showed up in a single dramatic instant. It emerged slowly, across years of painstaking analysis, as scientists compared Voyager 1's Heliopause crossing in 2012 with Voyager 2's crossing in 2018, cross-checking the 2 independent datasets against each other to make sure the temperatures, the magnetic alignment, and the plasma density spikes weren't some fluke of a single instrument or a single spacecraft. Having 2 probes cross the same boundary at 2 different locations, 6 years apart, is what gave scientists the confidence to say this wasn't a one-off anomaly. It was a real, consistent physical structure surrounding our entire solar system, and it behaved the same way in 2 very different places. Subscribe now if you want to keep following this story as the Big Bang upgrade attempt approaches on Voyager 1 in the second half of 2026. And as IMAP continues building its own map of the Heliosphere using the Heliopause data Voyager established directly. Drop a comment telling me what surprised you most about what Voyager 1 actually found at the edge of our solar system. The Kelvin that turned out to be completely harmless because the plasma is too sparse to transfer that heat. The discovery that the magnetic field just outside the Heliopause is aligned with the field inside the Heliosphere, rather than pointing in a random galactic direction. The fact that the Heliopause itself breathes in and out as the solar cycle waxes and wanes over 11 years, or simply the quietly extraordinary fact that a spacecraft launched 49 years ago passed through this wall, survived it completely unharmed, and is still sending home data from the other side. Thanks so much for watching all the way through to the very end. I'll see you in the next one.